Dr. Windring. He's a senior product manager from NVIDIA Alchemy. He's also an organic and polymer chemist by training and received his PhD from MIT, where he discovered a new class of dynamic covalent chemistry. He's also a scientist entrepreneur with experience commercializing a novel polymer technology. And before joining NVIDIA, he was an associate partner at McKinsey, where he advised chemicals and technology companies on growth and innovation topics. And with this, let's welcome. Thank you so much.
Hi everyone, very excited to be here. And thanks for the kind introduction. So maybe I can just go to the next slide. So as many of you know, the chemical and material industry is a massive one, some $5.7 trillion, about 5% of global GDP. And the chemical world is actually very diverse, right? So you have the basic chemicals all the way on the left, where you are just talking about feedstock, whether that's, organic or inorganic materials. You have your plastic fibers, in the second column, and then there's also a lot of diversity of specialty chemicals, whether that's electronic materials like semiconductor, OLED, batteries, paints and coatings, fragrance and flavors, catalysts, and then all the way on the right you have like your agrochemicals and so on. And what I think is very exciting, and I'm sure everyone from here would appreciate, is that chemicals plays a crucial role in our day-to-day lives. And over the last several years, there's just been an explosion in terms of how AI can help accelerate scientific discovery, specifically in this case in the chemistry and material science world. So if you see the plot on the left, around 2018 is where you see that exponential increase. And that a lot of this is driven by lots of great work in academia and both in and industry as well. Of course, there's materials project that originated here, and then there's also some leading work from various universities, whether it's CMU, and a bunch of other universities. And more interestingly, over the last few years, the big tech firms has been moving in this area. Of course, you have the Fundamental AI Research Meta Fair, where they have the Open Met or OMO database as released last year, for example, MetaGen or MetaSim from Microsoft Research, as well as the genome model from Google DeepMind. So a lot of work has happened in academia over the last 7 years. And more recently, over the last 2 years, there's just been major advances, not just in the AI models, but also in the data sets. They enables us, of course, to have better models and so on. One particular area that I would like to maybe focus our attention for today's seminar is on this particular class of AI surrogate models called Machine Learning Interatomic Potentials, or MLIP for short. These are AI surrogate models that approach quantum chemistry level accuracy, but are orders of magnitude faster. So on the plot that you see on the top left, of course you have your classical molecular dynamics simulation on the top left, where it's fast, so i.e. the computational cost is fairly modest, but there is significant error, it's not very accurate. And as you go progressively to the right, you of course improve in accuracy, but it comes with a trade-off of increased computational costs. So there's no like free lunch in the sense that if you want to improve accuracy, i.e. lower error, you need to increase your cost exponentially. And as we all know, in order to simulate accurately chemical systems, you usually need to simulate very large complex systems. And because of the computational bottleneck, you are often left to compromise on accuracy and generability. For example, you might be just using your classical force fields, empirical force field for simulating systems that are millions of atoms. It's hard to do, or it's impossible to do DFT simulation on system that large, without incurring too much cost. And here's where the interesting thing come in with these MLIPs. Given that they are AI surrogate models that's trained on, say, DFT data, for example, you approach DFT level accuracy, but a few orders of magnitude, if not several orders of magnitude, much faster. And that's sort of how we show the green dot over there. And of course, it approached quantum chemistry accuracy with at near classical force field costs. And some of the most useful computational workloads that we observed is molecular dynamics, of course, and as well as geometry relaxation. And sort of that's sort of the conceptual backdrop. And a lot of what I come from is from a product background, specifically this product we call NVIDIA Alchemy, which stands for AI Lab for Chemistry and Materials Innovation. It's focused on being the AI platform of choice for accelerating chemical and materials discovery with some of our product offerings. So the talk that you're going to hear is more from an engineering/product point of view, more so than on the scientific front. And the materials that are of interest for this talk is really materials that is like non-drugs. So it's things that go into a battery, catalyst, all that organic light emitting diodes, as well as even beauty products. So there's sort of like the way to think about it is that there's sort of two layers of offerings, targeting different audience, of course. So we have something called NIMS, NVIDIA Inference Microservice. This is a scalable layer of cloud-ready microservices for chemistry and material science and enable deployment and orchestration on the full NVIDIA accelerated computing stack. These are targeted more for the researchers who want out-of-the-box GPU accelerated simulations. And the way you can think about this is that if you are, preparing if you want to have like lunch, you can have a packaged meal that is an opinionated way of, having the meal prepared. And of course, the meal is prepared in an optimal accelerated fashion, if you may. But you need not necessarily want to consume that particular meal because you might not like, the protein or what have you not. So what we have is we can expose the building block, i.e. the ingredients. And this is what we have in the second layer called toolkits. This is a collection of GPU accelerated batch kernels and tools for training MLIPs, as well as for running accelerated batch or atomistic simulation with MLIPs. So these are the names that you see here are the prepared meals. And then the toolkit, you can think of them as building blocks or i.e. ingredients that you can actually use to generate your own simulation workflow or train your own MLIP.
So you are different to better than GPU bundle. This job in the Microsoft or Amazon cloud or better I use your cloud.
So the tools, the products that we produce are for, it is agnostic to where you run or your compute. It can be, a desktop or a workstation or GPU or a data center grade or GPU. So one thing caveat, of course, is a lot of the software that NVIDIA builds is specifically for our hardware stack, our accelerated computing stack. So it's specific to NVIDIA GPUs, but it is agnostic to whether you have a workstation or just a DGX Spark, which is your desktop supercomputer, or a data center grade GPU. So that's a great question. You can all of these tools run on any GPUs you find, NVIDIA GPUs. So the way to think about us is that we are building on top of the AI model from academia, from the big tech firms, leveraging our CUDA-X libraries. The middle layer that you see here is the NVIDIA Alchemy stack. We have the NIMS and microservices, and we want to support the community code developers, the independent software vendors, the AI first startups, as well as the broader industry as well. In terms of like the persona that we hope to benefit to support will be the researchers, the computational chemists and material scientists in both industry and materials. And typically we see them as requiring atomistic simulation that requires high level of accuracy to help inform chemical and material discovery, much like what this institute aspires to do. And then the other set of persona are the developers, the people who are actually building these tools for the computational chemists and material scientists. So this can include, community code like TOTC, MacGL, different independent software vendors, and increasingly these AI first startups. we noticed that over the last 2 years, there's just been an explosion in startups, raising fairly large sum of money to start their business. And for example, and NVIDIA has invested in several of them, most notably Periodic Labs that raised, $300 million at, unicorn status. So a lot of very exciting things that's happening, not just in academia, but also in the startup ecosystem as well. And NVIDIA Alchemy hopes to support the ecosystem, whether it is, academia, startup, or, broader, commercial systems. And the way to think about the names and microservice, if you the names and the toolkit is that they are actually synergistic. At the top you have the names where it serves primarily researchers, and the plan is to what we aspire to do is we want to demonstrate speed of light simulation and inspire new use cases, and I'll highlight a few use cases with some of our partners. And by building these microservice, these names, it actually inform what are some of the lower level building blocks that we need to build, those tools that we call toolkit, to enable speed of light simulation. And of course, these toolkits that we build, the hope is to accelerate developer platforms, whether it's in the community code developers or with some of these independent software vendors or AI first startups. And then, of course, whatever that we have at the toolkit will in turn synergistically accelerate some of our microservice performance as well. So maybe it's helpful to maybe at this point in time to talk about some of the work that we have done with these industry and customers. So maybe I'll focus on the middle and the right one first. So we work with Universal Display Corporation, UDC. They are actually the unsung hero of OLED. From what I heard, 99% of all OLED device actually contains that technology. And the only reason why, perhaps the next generation of iPhone is foldable is because it's made of OLED materials, because it's flexible. And of course, SES AI is a AI first battery innovator, and we have been helping them use atomistic simulation with MLIP to simulate different properties. For UDC, we were simulating thermal processing stability, and then for SES AI, we were trying to simulate some electronic properties for battery electrolytes. Of course, we managed to have a significant acceleration of at least a few more orders of magnitude faster than DFT with our toolings and with the inherent acceleration of MLIP in general. And what I wanted to actually focus our attention on is some of the recent work that we have with INEOS, which is the largest energy company in Japan. We did 2 projects with them, one on the OER catalyst, the oxygen evolution reaction. It is the side of the electrode that generates oxygen in the splitting of water from water to hydrogen and oxygen. And it's, of course, critically important for hydrogen production. And then we also help them develop new immersion cooling fluids for data centers. What's exciting is that, in addition, the first 2 examples that I highlighted is about accelerating existing computational workload. But just because you simulate something faster doesn't mean that what you simulate is actually useful. And in my mind, what is really useful is to help the experimentalists to come up with better materials in silico. And if you can come up with a better material, I think that is you demonstrate utility, not just speed. And that's actually what we actually managed to achieve is in working with INEOS, we actually identified 100 very promising OER catalysts in call it six months. Some of these catalysts that we proposed, the 100 plus, includes, of course, well-established OER catalysts, which not novel, but at least it validates our screening strategy. But what's exceptional is that the other remaining ones, call it 60-70% of them, actually contains surprisingly high potential candidates that when you surface to the experimentalists, they saw that, wow, that's a great idea. We should definitely validate in the lab. Of course, they wouldn't reveal it. Yeah, I mean, if it's good, which is why they are actually validating in the lab right now. They are actually doing it right now, and I think we are going to get some initial results in the next 1 or 2 months. So there are two, I think between that 100 plus candidates, around 70% are metal containing, so like metal oxides or ish materials, and then the other 30% are actually contains non-metallic elements. They are non-metallic, not organic. Yeah. So what I think is helpful is to make sure that I think what satisfies me as a synthetic chemist by training is that we are using computational chemistry, not just like NVIDIA. We can, of course, within NVIDIA, we can make simulation go fast. A few orders of magnitude, 100,000, 10,000x is not surprising to us. But I think what I encourage my product and the team to do is to make sure that we want to create tools that can help the scientists make new discovery faster. And to do that, the simulation needs to be useful. And I think this is an early indication of success, where we are actually doing something that is meaningful to that moves science, not just making simulation faster. So the MLIP that we use is trained on DFT data, so it approaches DFT level accuracy. And what I think is useful is that for the proposed candidates that we have, they are actually they are actually sending some of these samples for experimental validation. And so far, I think things are looking quite promising.
Basically, finding and compute the over.
Exactly. I think for this particular case, we use the machine learning interatomic potential, the MLIPs, to simulate the absorption energy of these three intermediates, the OH, O, and OOH species. And I don't have the figure here, but essentially, for the OER catalyst itself, the bottleneck is such that you want each of these steps to be sort of equidistant to each other, and sort of the equidistant step is around 1.23 EV. So sort of one of the criteria that we apply is to simulate the absorption energy of these three reactive species and to see which candidates provides the absorption energy that's closest to this ideal step where it's equidistant, such that none of this step becomes the bottleneck.
Can discuss later, but 16.
I think that might be some simplifying assumptions, but for the most important thing to mention is that we build tools, we don't do research. So we build tools that we hand off to the researcher and say INEOS to run. So that's the approach that they take it. I'm sure there are better approaches out there. Cool. So maybe with that, maybe we can look at, the first top layer, which will be broadly relevant for the researchers. So these are called NVIDIA Inference Microservice, NIMs. This is for out-of-the-box accelerated simulations. And increasingly, because each of them is a container with an API that potentially an AI agent can make a call to, we see NIMs as increasingly important for agentic workflows as well. And so simplistically, you have the requests that come into this Docker container, NVIDIA ALCHEMI NIMs. Of course, there's the API service, the input-output queue. And then we build our own simulation engine as well. It's packaged as a Docker container with a HTTP API. It's fully asynchronous with dynamic batching, so you get optimal GPU utilization, as well as load balancing across the multiple GPUs as well. We accelerated two things. One is the models. We pick a few MLIPs that we know are popular, and we use NVIDIA tools to accelerate them. And then we also have the surrounding peripheral simulation tools to make sure that those are running at the speed of light. And then we also have a unified model interface where folks can bring their own models. with the same architecture in it. So in terms of the names that we have available for evaluation right now, there's 3, and then 2 of them will be generally available starting next month. One for geometry relaxation, the other one for doing molecular dynamics, and then we have one for doing conformer search, and I'll go into a lot more details with that later on. And then for those that are under development, we are building one for transition state search with band, as well as one for metadynamics as well. And then in terms of models that we support, we have Maze, InNet2, and TensorNet. And we have plans for incorporating maybe a few more models, the OP model from Orbital Materials, UMA from Meta, FACAM, and then DPA from DP Tech. Yeah.
So you mentioned bring your own model, but so when you mentioned this model,
So in order for you to bring your own model, we will need to have the wrapper of the model built in. So you'll be able to bring your own like fine-tune Maze or InNet2 in order to, and it's actually not that hard to actually build to use the name by itself and then build a wrapper for your model. That requires some incremental engineering work. But we realize that there's just a lot of MLIPs. There's like one that comes out every few weeks. We cannot just keep up and keep adding new wrappers. It will just make the microservice cumbersome, which is why we are gravitating towards those MLIP that we see good but popular models out there. So the one that we have supported right now, and then those plans are those that in talking to the community, those are models that have been flagged to us as being quite popular. And if you have one particular MLIP that you have interest in, do let us know, and we'll collect requirements from you guys.
Support things like
Hmm?
you support things like the
So the UMA model would be the one from from Meta FACAM, and it is in the works. We do not have the wrapper for that model right now, but it is planned. It's likely the next model we have wrappers for.
The torch sim for radical also does batch change. You maybe just compare this versus torch sim and what
The spirit is very similar, and in fact, we have been, when I go into the later talk, we are actually accelerating torch sim from underneath. So we have something called Alchemy Toolkit Ops. Torch sim has integrated our neighbors list, and then they have plans to integrate our DFT-D3 or dispersion corrections as well. So the idea here is that we want to we want to be the rising tide. We want to raise all boats. We love all our partners, and we will never compete. NVIDIA will never compete with our partners. So TalkSim is a open source community code developer that we are accelerating from underneath. The spirit is the same. Like doing back simulation that is GPU accelerated. TalkSim is a great code, but there are places where it could be accelerated, and we are working with the TalkSim developers to make sure that their code runs well. And we are doing the same with MatGL and AMAT Central as well.
For your DFT code, so you are using VASP? Is it like a wrapper of VASP, or is it DFT code?
Yeah, so it's for the microservice that we have for the DFT one. So we have one for VAS, one for GPU for PySCF. The one with VAS, it is like bring your own VAS license. It's really just a container that allows you to do what we call MPS, multi-process service. So essentially, if you're running a small system on VAS that is below 40 atoms, you're not fully saturating a given GPU. So by doing MPS, you can actually saturate your GPU better. That I have some of the data for GPU PyCF that help illustrates that. Cool. Any other question? If not, maybe I can do a deep dive into some of these microservices that we have and show a workflow of how we enable different the end industry customer to do some of this work. Great. So for geometry relaxation, we'll have the general availability name on our NVIDIA MGC catalog next month. So the whole idea here is that the as-is ways of doing simulation is on the left, where you will likely run your MLIP like AIMnet2 on GPU. And then you will do the simulation itself in like ASE, for example, it's very popular. It's atomic simulation environment. And because of the GPU, CPU communication overhead, it is slow. And then you do things one molecule at a time, so there's no batching. So what we try to do, with three simple tricks, we are able to get pretty good performance. I think the first trick is we run everything on GPU, so there's no communication overhead. The second is that we use Warp, which is a Python developer framework from NVIDIA, to ensure that you get high performance simulation. It's just a language that is really good. It's PyTorch based, and then we do something called in-flight batching. So do things in parallel, and as soon as one system is complete, one simulation system is complete, you swap it in with a new system to run. So a bit of benchmark data. This is actually a bit data. We have accelerated this a lot more. So it will be much faster. The microservice that we have now will be much faster than 20 to 60x. But using this old data, you can see that with the baseline of like comparison is with ASE Fire, which is the dark gray one here. That's sort of the baseline that we benchmark against. We see around 20 to 60x acceleration. And a lot of this acceleration, it depends on, the system size you're running. This is using AIMnet2, so we are looking at molecules. You see, you get 60x if you have on average 30 atoms in your molecule, and that becomes 20x when it's around 100 atoms. A lot of this acceleration comes from sort of two places. The optimizer that we have takes fewer number of steps to converge. And then the time per step is also faster. So that's why you get, that 20 to 60x acceleration. And we also fine-tune the optimizer such that optimizing it not just for performance, but also for convergence. So you see actually pretty good convergence, near 100% convergence for our Alchemy Fire 2 optimizer versus maybe the other optimizers that's out there. So that's I think there's a few things here, but the optimizer will be over here. I think it's mainly the optimizer and then also removing the GPU CPU communication overhead by running everything on GPU.
Big space, then you imagine a very large. That's it. The overhead patch.
So it really depends on the system size. As you increase the system size, you get diminishing in you will get smaller acceleration, as you see over here as well. When you move from 30 atoms to 100 atoms, you will see diminishing in acceleration. And I think the whole idea here is that it really, and maybe the next slide will actually provide a bit more illustration as well. There is benefit for sure in there's even modest benefit in running like a single large systems, but you get a lot more throughput if you're running multiple small to medium sized systems. So if you're doing high throughput screening of materials, I think that is a great use case.
What's the difference between your optimizer Fire 2 and the one of ASE? Because I see the conversion structure, there is a huge gap for like it's 16% and 100% is connected.
Yeah, so our engineering team did, some magic on the optimizer. I don't really know what exactly he did, but we did optimize the optimizer for not just performance, but also for full convergence.
But is it because of the number of steps? You have a fixed number of steps, and because like the 16% that didn't converge after a certain number of steps, or is it just because of the optimizer is a bit better?
I think the optimizer is better. Okay. Yeah. So that's geometry relaxation, and then we have one for molecular dynamics as well. So in this case, it's focused on the material side of things. We use the OMAD24 data set. We have two models, MACE MPA0, that is accelerated with NVIDIA co-equivariance. And then we also have some custom kernels for TensorNet. We are very excited to also, I don't know whether the PR is approved yet, but we actually submitted our Warp kernels to the MATGL implementation of TensorNet. And that PR, I think, is going through. I think we observe, I think, 7x acceleration of TensorNet using our warp kernel. So anyway, two models that's quite popular. We accelerated the model itself with co-equivariance and with our warp acceleration respectively. And then on top of that, we also accelerate the simulation tools that's around the model itself. That includes like the integrators, for example. And what you see is plotted here on the vertical axis is time per atom per step. So the lower the number, the better. And you'll see, of course, that as you increase the system size, the total number of atoms that's simulated in the system, which is, of course, a function of number of, I believe over here. Yeah, which is essentially a like number of batches that you run in parallel, and the number of atoms per batch is what you plot over here in the horizontal axis. And as you simulate a larger like total number of atoms, you see an exponential decrease in terms of the time per atom per step. Not surprisingly, if you use newer generation of GPUs, you get better performance. You see, you get from 6.8 microseconds to 2.2 microseconds from moving from an A100 to a B200. And what's interesting is that you get to simulate larger system as well because you have more memory. Usually, the reason why you only get, call it 40,000 atoms over here is because you run out of memory with a 40 gigabyte memory. So that's that. And then for TensorNet, we can actually go even further. We get to around 1.4 microsecond, and we get to simulate, on a single GPU for B200, you get to more than 350,000 atoms in a single GPU. So that's for molecular dynamics. And then the last microservice on with MLIP that I want to just show here is just for conformer search. The whole idea that you have a molecule with rotatable bonds. Of course, there are many different conformers that exist, and the number of conformers options increases as you have more rotatable bonds. The plot that we want to show here is just to demonstrate that in order to make sure that you have identified all the conformers within a certain energy threshold of say 3 kcal per mole, if you have like two rotatable bonds, if you simulate say 10 conformers, you have a 92% chance that if all your molecules are within that threshold of 3 kcal per mole, and if you of course generate 100 conformers for a given molecule, you are close to getting all of these molecules within that threshold of 3 kcal per mole. As you increase the number of rotatable bonds, intuitively you know that you need to generate more conformers to make sure that they all fall within that success rate of like 3 kcal per mole. Of course, that's just an arbitrary number that we use. So what we want to demonstrate here is that as your molecule become larger, more complex, you need to generate more conformers, which means that you need an efficient way to generate your conformers and relaxing it in an efficient way. And that's why we have the batch conformer search name that is helpful. On average, the average optimization time per conformer on a H100 GPU is about 10 to 100 milliseconds. So that's quite fast. And this actually helps encourage, like when we talk to people in industry, many a times they don't actually consider conformers in their chemistry because it's just too computationally expensive to do it via DFT all the time. You just use the lowest energy state. But of course, that's not realistic because at room temperature, there's a range of thermally accessible conformers that's available. And these microservices will solve that problem by allowing them to simulate low energy conformers rapidly. I think there was some question about the MPS, the microservice service for doing like running DFT. So what you have on the left and the right are the same data. It's just what you plot. The left is just average time per task, and then by benchmarking the speed up in terms of a number of speed up, we baseline that for one MPS thread to be the baseline. And what we see here is that as you increase the number of MPS threads doing things in parallel, assuming that you have say 40 atoms, you get progressively between 3 to 4x acceleration for 40 atom systems. And of course, if you increase the number of size of atom this dimension, the acceleration become more moderate, say by between 2 to 3x. And that's because if you have a larger atom, you are more likely to saturate your GPU already. So that's the intuition. We get 3 to 4x if you're doing GGA, around 1.5x if you're doing a hybrid DFT. So that's a quick overview of the microservices. I'll just quickly run through some of the case studies. So as I mentioned, we work with Universal Display Corporation that makes who is the innovator in OLEDs. In this simple workflow, we start with, they shortlisted 10,000 candidates. We help them generate 100 conformers for each of this molecule. For each of these conformer, we help them. What they did is they pack it into a simulation cell and they try to run molecular dynamics at increasing temperature. And at a certain temperature, things will start falling apart from each other. And that's where it helps sort of describe the temperature for the thermal processing stability is sort of the property that we are helping them with. And then you can, of course, do it in an iterative fashion to like fine-tune, different substituent on your molecule until you find your optimal OLED materials. So that's just a simple way of piecing together different of these microservices in the workflow to simulate some useful properties. And I think what's interesting is that if you think about this simple workflow, it's actually easy to have an AI agent to orchestrate the use of different microservices. And that's why I think these microservices is also a useful way to run speed-up simulation if you want to like orchestrate it with some AI agent. I'll just show another simple example where we work with SES AI to simulate electronic properties of these battery electrolytes. We start by, for a given molecule, find the lowest energy state using our batch geometry relaxation microservice. And then we use the GPU for PySCF microservice to calculate the HOMO, LUMO, as well as the electrostatic potentials. And then help them to create the world's largest battery materials data set for electrolytes. And then they also augmented not just the quantitative information, they actually train on a lot of chemistry literature to generate this chemistry LLM that's trained on the NVIDIA NeMo framework for LLMs, as well as on our DGX cloud service to create this database that have not just qualitative information from the LLM, but also quantitative information from alchemy simulation. And then, of course, we have some data visualization work with cuML for doing UMAP. So that's just another use case. I know I'm running out of time, so I will just quickly go through the next few slides. So this is just, we talk about the names a lot, and I'm going to just pivot into some of the lower stuff because I think there are developers here that will find the lower level stuff useful. Names is, the microservices, but the toolkits are building blocks that you can build your own simulation engine that's running at the speed of light. So we have the middle layer toolkit that we will release we'll release the GitHub repo next month. So please keep an eye on that. That will be a collection of modular training, simulation, and active learning workflows. And then the bottom layer is actually public. It's called Alchemy Toolkit Ops. It's a collection of accelerated kernels. And that's the one that I wanted to maybe spend a bit more time on today. And specifically, we realized that users, whether you're researchers or developers, we want to access the NVIDIA stack at different level, which is why we have this tiered sort of engineering strategy where we create offerings at different levels so that depending on whether you want to build your own simulation engine from scratch, then you want to access it at the lowest level. If you are like a researcher that just want to run simulation to help inform your experimental work, you can probably use the top layer of the microservice. So Alchemy Toolkit Ops is already public. That's the GitHub link. And right now in our public beta, we have sort of three things. We have two neighbors list, one cell, and then one naive. We also have DFT-D3 dispersion corrections, as well as long-range electrostatic, specifically EWOSUM and PME. As mentioned earlier, we have been integrating our NVIDIA ALCHEMI toolkits with leading open source codes, TOTC, MatGL, IMNet Central. I think all three of them have at least integrated our batch neighbors list. And I believe IMNet Central also integrated our DFT-D3 correction already. And we are actually working with a number of leading independent software vendors to accelerate their offerings to enable the broader ecosystem. And then next month we'll have an updated release. We'll have some accelerated dynamics kernels, including like thermostat, optimizer, and integrators. And then we will also start providing JAX support. Right now they are written in Warp, so they are native PyTorch, but we will start having JAX support as well, given that we see some interest among the community. So I'm going to just show some slides to show some benchmark of the performance. So the blue band that you see is typically the time per atom for running MLIP. So that's neighbor space, which is the pre-processing step before you expose it to MLIP, is usually quite slow. So what we have done in talking to a lot of folks in the community, we realized that neighbors list is a bottleneck. So what we have done here is to accelerate the neighbors list such that it's significantly faster than the MLIP. So such that it's no longer the bottleneck. We did some benchmark at different radial cutoff, 6, 15 and 25, and of course with larger cutoff it takes the time per atom is higher. And then we have two implementation, the naive and the cell list. The naive is usually good for lower systems, like smaller system size, and then the cell list is typically better for larger system size. And the way to read this graph, I know it's a bit complex, is that we fix the number of total atoms to 128,000 atoms, but we vary the system and batch size. So in the extreme right, it's just one system with 128,000 atoms. On the extreme left, you have the batch size, i.e. you are running 1,024 system in parallel. Each system is 128 atoms. So that's maybe the way to read this plot. We provide this plot so that depending on the type of system you are running, you have an indication of knowing what is the neighbors list or compute time, and you can decide which method to use, naive or cell, depending on your system. We did the same thing, but in this case with DFT-D3, some changes here. There's only one batch, so i.e. one system, and then we progressively increase the number of atoms within that system itself from 128 to 128,000 atoms within that. Over here, I think there's still significant room for making DFT-D3 more performance, because right now I think it's in the same order of magnitude as the underlying MLIP. And our team is actually working right now. I think within the next maybe 4 or 5 months, we'll have an accelerated version of this DFT-D3 that will be potentially an order of magnitude faster. But I think this is already better because I think DFT-D3 is traditionally slow. And then we have some benchmark for electrostatic. Suffice to say, like for the electrostatic, whether we are doing EWO or PME, I think we are significantly faster than the MLIP. So that's great. And depending on the system sizes that you have, you can decide whether EWO method or the PME method is better. With EWO summation being better for my small system sizes, and then PME, of course, being better for the larger one. And we have include different accuracy threshold, whether that's 10 to the power -4 or 10 to the power of -6. So that's, that all this is in the tech blog that we have already online if you want to review it. And then the last thing, maybe I will just end with these 2 slides. We do have a release next month as well on this middle layer of Alchemy toolkit. It will have of course, the data classes and data loaders over here. We'll have wrappers for, the stream models that we mentioned earlier, with some of the wrappers for the physics-based model like the FDD3 as well as the electrostatic stuff. We'll have a composable batch simulation pipeline, as well as with all these simulation protocols like optimization, dynamics, NEB, and it will have like in-flight batching included in it as well. And then of course we'll have some training utilities and active learning abstractions that will allow you to actually generate your own simulation and simulation and training / active learning pipeline. And then with that, I'll just end on this slide. There's some links to our GitHub repo that went live just in December, and we are getting very good traction from the community, including some tech blogs in case helpful. And then I would strongly encourage you guys to maybe about a month's time, we'll have a new release for all three things. So we will have an updated release for our GitHub repo with the dynamic kernels and JAX bindings. For the microservice, we are finally live with 2 of our microservices, one for geometry relaxation and one for molecular dynamics. And then for Alchemy Toolkit, we'll have the release that includes the components that we have here. So with that, I'm happy to take any question for the last 3 minutes.